Hey fam, this is our lesson for Z-scores. Z-scores is going to be one of the most important things that we learn all year. I'm smiling because I'm realizing that I say that a ton. But quite honestly, if I can think about some of the really big themes or ideas that always show up on the AP test and some things that we need to be prepared for. It was SOX, describing a distribution, so shape, center, spread, outliers. And next would be Z-scores, which is highly related to standard deviation. In fact, it's based off of standard deviation, and then the normal distribution. So three really big ideas, all within this time frame. We just did SOX, and now we're going to do Z-scores, and next time we're going to do normal distribution. So Z-scores, we use them so much. In our next unit, we use Z-scores for the entire unit. So this is something that we want to make sure that you understand, that you feel comfortable calculating, and that you can interpret it and use it to answer questions. So without further ado, I just want to briefly, sorry, what's going on here? I just want to briefly revisit what standard deviation is. So standard deviation tells you the typical distance that the values in a data set are from the mean. So we have a bunch of observations. We figure out on average how far away from the mean are the rest of our observations. And this visual is a very important and I think helpful visual. So standard deviation that is large is data values that are spread out from the mean. Remember that your flagpole is the mean. And standard deviation that is small is data values that are clustered around the mean, like this visual here on the right. If we're speaking in general of data sets, we want a smaller standard deviation. A smaller standard deviation is better because it's going to allow us to make predictions and inferences from our data, because our data is what we would consider more reliable. This data set is so spread out, we would consider it less reliable. It would be a little bit harder for us to make predictions. And I'm hoping that you looking at these visuals, it helps you see that. If we make a prediction with this data set, I think that we can feel pretty comfortable that our prediction is going to be fairly accurate. If we make a prediction with this data set, because it's so spread out, we're probably going to be less accurate. So let's say that I have a data set from last year's AP Stats classes, and the data set is the scores that they got on the AP exam at the end of the year. So if I get that data set back and all of my kids' scores from last year look like this, then I'm gonna have a hard time predicting what your scores will be if I have this data set, because you can see I have some people right around the middle, which would probably be like a 3, and then I have some people way on the left and way on the right. So if I'm trying to predict your score based off of this data set, I could predict that you're going to be a 3, but look at how many people are not a 3, how many people are very far spread out from a 3. Whereas with this data set, if I predict you're a 3, you'd probably feel more comfortable that you are going to get a 3, because most of the data is clustered around the same value. So I'm hoping that that makes a little bit more, a little bit of sense, a little bit more sense about why standard deviation is so important and why we want a small standard deviation as opposed to a big standard deviation. This allows us to feel comfortable with predictions and inferences. This makes us less comfortable with predictions and inferences because it's so spread out. This is clustered very nicely. So that was the basic idea. Then we spent most of the time learning how to calculate standard deviation. And that's where we really go through, find the distance that every data value is from the mean, and then average out that distance. Remember, though, that we need to square the difference, because if we just add them here to find the average, it all cancels out, and that makes it more, that makes it so that we can't calculate the standard deviation. So we had a data set of 11 points, and you can see here that if you're getting anything past 10, if your set of data is anything past 10 observations, this process of calculating standard deviation is very, very cumbersome. You're probably not going to want to do it for anything bigger than this one here. So it's really good that if we wanted to, we can find standard deviation using one variable stats in our calculator. And I'm wondering if I have written that anywhere. So I'm going to write that down really quick, that your calculator will do this. And it's stat calc option 1, which is one variable stats. And if you have the data set, you enter that into a list, and your calculator automatically does all of this for you. 6 minutes reviewing. Sorry. Hopefully this isn't horrible. And then the last really important thing is interpreting standard deviation. When you interpret standard deviation, they want you to interpret it exactly like it's written here and exactly like you practiced on this reverse side. They don't want you to use any other words. They want it to be written like this so that they can be sure that you understand standard deviation. The one thing that I want to make sure that we all know is that standard deviation, so one standard deviation below the mean and one standard deviation above the mean will include most of our data values. So when we say the number of friends typically varies from about 1.34 friends from a mean of 3, we can also then interpret that as most students have between 1.6 and 4.3 friends. So you take your mean, and if you subtract one standard deviation and add one standard deviation, that tells you where most of your data lies. So over here, most frogs live between 14 months and 22 months. Most pathfinders last between 90,000 and 110,000 miles. Not all of them, but most. And most would be a percent over 50. So that's the last review item that I would like to go over, is that when we interpret standard deviation, they don't necessarily want us to write this, but most of the data will be between your mean plus or minus one standard deviation. So that's not what they want us to write. They want us to write the number of friends typically varies by the standard deviation from the mean. But in our brains, what we have to make sure that we understand is that's telling us where most of our data values lie. So that took me 10 years to recap. I'm sorry if that was very cumbersome for you. Biggest takeaways: more spread out, less spread out. The calculation is pretty crazy, but our calculator will do it. There is a specific way they want us to interpret standard deviation, but what we really need to know is behind that interpretation, what we're saying is this. Okay, so the reason why I spent so much time going through that is because z-scores are based off of standard deviation. So now we're moving into this new lesson sheet, and this is z-scores. So z-scores tell us how many standard deviations from the mean an observation falls and in what direction. So observations that are smaller than the mean have a negative z-score, and observations that are larger than the mean have a positive z-score. So negative observations are below or smaller, larger is above, and that will be positive. So smaller or below the mean, larger or above the mean. So a z-score is going to tell us how far is a specific observation from the mean in terms of standard deviations. So a better way to say that is how many standard deviations from the mean is a specific observation. Converting observations from original values to standard deviation units is known as standardizing. Now, what I want you to recognize is that the word standard deviation and the word standardizing, those match. It's called standardizing because you are figuring out how many standard deviations you are from the mean. So instead of calling it standard deviation units, we are going to shorten that down and call it a z-score. It's called a z-score. So a z-score is telling you how many standard deviations a specific observation is from the mean. And then it gives you the formula. So you take the observation, the specific observation. So maybe I should write that down. This is the given observation. You subtract the mean and you divide it by the standard deviation. The formula that we will see most often, instead of words, it will look like this or the one next to it. So this is saying the same thing. Your given observation, subtract your mean, divide by your standard deviation. So let's just look at a specific example to enhance our understanding of what a z-score is. The figure below shows a dot plot of a class's height distribution along with summary statistics. So we get the dot plot and we get the summary statistics. And the first thing that I'd like to note on this is that this data to me seems pretty spread out. I personally think this data is pretty spread out. So if I go to find my standard deviation in my summary statistics, they give us that the standard deviation is 4.29. Which, I don't know, that doesn't seem, well, let's think about it. In terms of height, is 4.29 inches a big deal? I think the answer is yes. Because somebody that's 4 inches taller than me is 6'2". That seems ginormously tall. And somebody that is 4 inches shorter than me personally is 5'4". And that's a little short. So I do think that a standard deviation of 4 inches is pretty spread out. The other piece of really important information that this gives us is our mean. Our mean is 67. So on average, people are 67 inches tall. I think that's 5'7", with a standard deviation of 4.29. So I want you guys to take a second and I want you to write down what most people in this data set are between. Most people are between. You take a second to figure out what the heights are. Really do it. So this is based off of what we did last time. Okay, if you're not done, pause. We would do 67 minus 4.29. So 6271, and we would do 67 plus 4.29, 7129 inches. So this is 5'2", and no, that doesn't seem right. Almost 6 inches, right? Yeah, this is 5'2" and 6'11". When I say most people, what I mean is so I should have just circled people. When I say people, I mean these people in the dot plot. So most of these people are between 62 and 71. Well, now I'm curious to see if that's really true, and if it's not, I'm going to have to stop this video and re-record. So please bless that I'm right. Okay, so 62, we would have to go a little bit above that 62. And 71, so we would go here. Okay, let's figure out if I'm really right on this statement. 1, 2, 3, 4, 5, 6, 7, 8. So 17 out of the 25 people in this class were between these heights. Let's see if that's most. Booyah, teacher, it is. That ends up being 68%. And 68% is most. If you have bigger than 50, it's most. Okay, so sorry for taking us down that rabbit hole, but I think it's important to understand. Okay, so now that we know that most people are between 62 and 71, let's standardize some people's heights so that we know how far away from the mean in terms of standard deviation these people are. And here's why. Because if we find a z-score and you're within 1 standard deviation, then that tells us something about your height. That tells us where your height falls. That tells us that you're, I don't know, quote unquote normal. If you're like 2 standard deviations away from the mean, you're a giant. And if you're like 3 standard deviations below the mean, you're very, very short. So telling somebody or figuring out how many standard deviations away from the mean something is does give us information about that observation. Okay, back to business. So Shelby, this is for Shelby Green. Sometimes I change the names of the students in my note sheets to kids that I love. So Shelby, a student in the class, is 65 inches tall. Find and interpret her z-score. I don't really know if she's 65 inches tall. So z-score equals, and then we got to use our formula. Well, actually, Famil, let's write down the information that we need. We are going to need x, we're going to need x bar, and we're going to need s of x. So x is the given observation, so that's Shelby's height, that would be 65. X bar is 67. Standard deviation is 4.29. These two are given in the summary statistics. If they wouldn't have given us summary statistics, we would have just plugged it in our calculator, and by it, I mean all of these data values. So I already forgot what I was saying, but X bar is the Shelby's height, the given height. X bar 67, standard deviation 4.29. We pull these from the summary statistics. Otherwise, we would have calculated it. Okay, now we calculate z-score. We take our given observation. How do I know? Because I'm up here on this green thing. Given observation, subtract our mean divided by our standard deviation. So when I plug this into my calculator, I'm personally going to do it in 2 steps. So I'm going to go 65 minus 67, enter, divided by 4.29, enter. Because if you just type it in all on one line, you don't get the same answer that I get. Your other option is to do green button, y equals, choose the fraction, and type it in as a fraction. So we are getting a z-score of 0.46. I usually round my z-scores so that it looks like money. And by money, I mean like this would have been 46 cents. That's just my preferred method of rounding. You use whatever you prefer. I would go at least 2 though. Go at least 2, if not 3. And now we need to interpret this z-score. So this is telling us that Shelby's height is 0.46. But wait, teacher, it's negative. That's coming up. Shelby's height is 0.46 standard deviations below the mean height of the class. So Shelby is shorter than the mean. Shelby is shorter than the mean by about half a standard deviation. So she's definitely within normal range. You do not put the negative because you put the word below. You wouldn't say she's negative 0.46 standard deviations below the mean. So in this case, our z-score was negative 0.46. And the interpretation is that Shelby is 0.46 standard deviations below the mean. This is how they want you to interpret z-score always. So I am going to highlight this box for myself. Okay, next up is another student, Ethan. This is for Ethan Cervantes. He's a great kid. He is 74 inches tall. How tall is Ethan compared with the rest of the class? Give appropriate numerical evidence to support your answer. Now, when they say compared to the rest of the class, what they are asking us to do is calculate z-score. When it says compared to the rest of the class, that's their way of saying calculate z-score. Because the z-score is going to tell us his height compared with the rest of the class. The average of the class is 67, and we're going to figure out how far away from that average is he in terms of standard deviation. Because remember, most kids are within 1 standard deviation. So if he's within 1, like Shelby, she's within 1, even though she's below, she's still within 1. Shelby's height is pretty normal. Shelby is pretty close to the mean. Let's figure out how close to the mean Ethan is. So our X is Ethan's height, 74. I don't really need to write down my X bar and my S of X again because it's the same data set. This is the same values that I would use here. So I can say that Z equals our given observation, subtract our mean, divided by our standard deviation. So we plug that in. And I'm getting 163. Okay, well, hopefully you're recognizing this means that Ethan is pretty tall compared to the rest of the class. He is outside of the range that most kids are. Most kids are within 1 standard deviation, but Ethan is 1.5 standard deviations away. So this is telling me that Ethan is taller than most of the class. How do I know? Because most of the class is within 1. So he is taller than most of the class. How do we interpret this z-score? Ethan's height is 1.63 standard deviations above the mean. So Shelby was in the height range that most students were in, but she was close to the mean. She was only about half a standard deviation away from the mean, whereas Ethan is taller than most of the class because he is not within 1 standard deviation. So just like on the last one, I'm going to highlight the interpretation. And now we have the foundation of a z-score. And the rest of this lesson is just learning to apply what we know about z-score. So, Ethan is a member of the school's basketball team. The mean height of the players on the team is 67 inches, and Ethan's height translates to a z-score of negative 0.85 in the team's height distribution. What is the standard deviation of the team members' heights? Okay, so this, what do they want us to do here? So let's walk through this together, see if we can figure out what's happening. First, I'm going to highlight the important information that they give us. They tell us that the mean height of the team, that's not the color that I want, the mean height of the team is 76, and Ethan has a z-score of 0.85. All right, well, how are we going to use this? Well, in our z-score formula, we are finding z based off of x, x bar, and standard deviation. Our z formula is made out of all of those things, these 4 things. So let's see what we have. We have z. They tell us that Ethan is negative 0.85 away. So let's pause here and let's make sure that you understand what this means. First of all, how does Ethan's height compare to the rest of the team? Just think about that in your brain. How does Ethan's height compare to the rest of the team? Okay, hopefully you're recognizing. He is within the height range that most students are. He is below the mean. He's below the mean and within the height that most of the players are. X is his height. His height from the previous problem was 74. The mean is 76. So the mean of the basketball team is much higher than the mean of the class. The mean of the class was only 67. The mean of the basketball players, much taller. The only thing that we don't know then is standard deviation. What is the standard deviation of the team's height? So now let's plug all of that in to our formula. Remember, our formula is z equals x minus x bar over s sub x. So we do this little sideways smiley thing because we don't want to put another equals. So we have negative 0.85 equals 74 minus 76 over S sub x. And now we rely on our knowledge of solving equations to find standard deviation. I need to get standard deviation out of the bottom here. In order to do that, I would multiply by S sub x. This is now S sub x over 1. And if you have a standard deviation in the bottom and a standard deviation in the top, those simplify. If you multiply by S sub x on the right side, you also have to do that on the left side. So now what we have is S sub x times negative 0.85 is equal to 74 minus 76, or you can just write negative 2. It's up to you. Okay, well now I want to get rid of this negative 0.85 so that S sub x is alone. How do we do that? We divide. So divide by negative 0.85 on both sides. Those will simplify. So S sub x is 74 minus 76 divided by negative 0.85. You plug it in. Don't just wait for me to give it to you. You plug it in. Okay, this is 2.35. So the heights on the basketball team vary more than the heights in the class. The heights in the basketball team vary more than the heights in the class. The class only varies by, oh, I'm lying. Oh, teacher, you're so dumb sometimes. Okay, sorry. The class's heights vary by 4 inches, but the basketball team's heights only vary by about 2 inches. All right, well, that would make sense to me. It would make sense that you probably have a lot of taller kids on the team. Like, it would make sense to me that most of the heights of the team are about the same. I wonder if we looked at like an NBA team, if like most of the players are about the same height. Whereas in a class, you have all types of heights. You have small people and tall people and everywhere in between. But on the basketball team, you're probably on the higher end. That's backwards to you. It doesn't matter. The higher end, and they're probably all about the same height. Okay, so that makes more sense to me. All right. Okay, you guys okay with that one? I hope you're okay. Okay, so this is it. This is the whole shebang. There's only one more thing, so I guess that means that's not it. Teacher, why? So we have one more thing that we can do with z-score, and then we are done. I keep zooming out thinking that's going to make my face smaller. Nope. Okay, so on this front side, we know what a z-score is now. We know how to use a z-score to compare an observation to the rest of the data set. And we now know how to use standard deviation to compare two data sets. So the classroom's height is more varied than the basketball player's heights, which should make sense. Okay, backside. This is one of my favorite problems we do all year. This is called the Home Run Kings problem. The single season home run record for Major League Baseball has been set just 3 times since Babe Ruth hit 60 home runs in 1927. Roger Maris hit 61, Mark McGwire hit 70, and Barry Bonds hit 73. In an absolute sense, Barry Bonds had the best performance of these 4 players because he hit the most home runs in a single season. However, in a relative sense, this may not be true. Baseball historians suggest that hitting a home run has been easier in some eras than others. This is due to many factors, including quality of batters and pitchers, hardness of the baseball, dimensions of the ballparks, and possible use of performance-enhancing drugs. So, the setup to this problem is we're looking at the 4 people that have scored the most home runs in Major League Baseball history. And I'm assuming that every single one of you guys have heard of Babe Ruth, because Babe Ruth was an exceptional baseball player, especially for his time. What do I mean by that? Well, nowadays, you have enhanced facilities to train. You have more knowledge about how to create the best athletes that exist. You have performance-enhancing drugs. The dimensions of the baseball fields have changed a little bit. So we can't really compare Babe Ruth from 1800s, just kidding, the 1920s, to the early 2000s. Like, those two worlds, those two United States are so different. So much changed in those 80 years. So instead of just saying, oh, well, Barry Bonds was the best, obviously Barry's the best, he hit the most, what we want to know is if everybody's conditions were the same, if everybody was on the same playing field, not literally, but figuratively, who would really be the best? So if we take into consideration that factors have changed and athletes are different and so on, would Barry Bonds still be the home run king? That's the setup. So to make a fair comparison, we should see how these performance rate relative to other hitters during the same year. To do this, we need to standardize their scores. So in order for us to put them all on a level playing field, no pun intended, in order for us to compare them and try to minimize the effect of the differences between the times, we're going to standardize their scores. So first of all, we need to know who each of these players is. The first one is Roger. Second one is Mark. Third one is Barry. Fourth one is Babe. And we are given the information that we need for each of these players. So if I'm going to standardize Roger's score, well, Roger, and you don't have to do this on all of these, Roger's number of home runs is, from the table, 61. The mean for his year in baseball was 18.8, so 18 home runs. So he definitely hit a lot of home runs compared to the mean. The standard deviation was 13.4. That is a very big standard deviation. Your standard deviation is almost as big as your mean. Okay, so we calculate his z-score. His z-score is going to be 61 minus 18.8 divided by 13.4. So Roger Maris, his z-score, if you plug that all in, is 3.15. That is very high. That is very, very mooey, extremely high. You're more than 3 standard deviations away from the mean. That basically means you did better than everybody, which he did. He scored the most home runs that year. So to score the most home runs, you needed to be more than 3 standard deviations away. So now you would do the same for Mark. Mark's number of home runs was, from the table, 70. That year, the league average was 20.7. So not that much more than Roger's year. And that was 40 years later. Maybe 30. 37 years later. Mark's standard deviation is 12.7. So still pretty high. So you guys pause the video and calculate z-score without me. Okay, Mark's z-score is 3.88. So right now we know in a relative sense, Mark did better than Roger. Mark was almost 4 standard deviations away from the mean in the late 90s. So compared to all of the other players at that time in our history, he was almost 4 standard deviations away from the mean. And Roger was only about 3 standard deviations away from the mean. So Mark, these two compared, Mark did better. Mark had or is between these two the home run king. Okay, now you find the z-scores for Barry and Babe. So pause the video because I'm not going to go through and give you all these numbers. You go through and find the z-score for Barry and Babe. Okay, Barry had a z-score of 3.90 and Babe had a z-score of 5.44. So who's the king? Who really is the home run king? Babe. Babe is definitely the home run king. Why? Because relative to everybody else in his time, relative to all the other players in 1927, he was 5.5 standard deviations away from everybody else that was playing under the same conditions. So Babe is truly the home run king. He was the most unusual out of all 4 of these athletes. Barry beat out Mark, but Babe beats everybody. So you compare their number of home runs to all the other people that were playing under the same conditions. And when you do that, it takes out the effect or minimizes the effect of the other factors such as changing dimensions, performance-enhancing drugs, all of that stuff. This is what you do the most with z-scores. You compare how people did relative to each other. Okay, one last problem and then you're done. In 2001, the same year that Barry Bonds set the home run record, Arizona Diamondback Mark Grace's home run total had a standardized score of -0.048. Determine the number of home runs he hit. So he was below the mean, but still within most players. So below the mean, but still within what most players were doing. One important piece of information is that this is the same year as Bonds. Why is that important? Because they want us to use the z-score formula to find a piece of missing information. So remember, z-score formula is calculated using 4 things. Let's figure out what things we have. We have z. We have X bar. We come up here to Barry's season. X bar was 73. S sub x is 21.4. That's a pretty big standard deviation. Wait, did I read that right? No. Oh, that sounded weird. Hopefully you guys hopefully you guys are sitting there like, what? Okay, sorry. I thought the mean of 73 was very high. Mean was 21.4. Standard deviation is 13.2. Still pretty high. What we don't know is Mark Grace's number of home runs. So we plug all of this into the z-score formula. Negative 0.48 equals Mark's home runs subtract 21.4 divided by 13.2. And we solve for x. Okay, well, I have to multiply both sides by 13.2. So these two simplify. And this side goes to negative 6.336. That is now equal to x minus 21.4. So to find x, we add 21.4 to both sides. And we get 15.064 equals x. So now we got to decide how many home runs that is, because typically in this case, we would round up to 16 because you can't have part of a home run. And usually if you get like 2.1, you always round up to 3. But because this is so close to 15, I decided to check whether it was 15 or 16. So what do I mean by that? I actually calculated the z-score if it were 16, and I calculated the z-score if his number of home runs was 15. So if you calculate z-score for home runs of 16, you get a z-score of negative 0.41. But if you calculate the z-score for 15, you get the z-score of negative 0.48. So I know for sure that it's 15 home runs. I don't think you're expected to do that on the AP exam. If you're unsure, just leave it as 15.064. But because I knew that I could do this, I could just go through and say, well, I know it's got to equal negative 0.48. So what does it equal if I plug in these values? I was able to decide it was 15 and not 16. Okay, so this is typically the point in which you stop, but I would like to use this time as an opportunity to help you figure out how you are supposed to use the solutions videos to help you with your Can You Do's. So pause and go and get your Can You Do. I'm going to pause and go get mine. Oh, I got to make myself little. Okay, so on your Can You Do number 7, I want you to try exercise 9. So now that you have your Can You Do in front of you, I want you to do number 9. The SAT versus the ACT. So I want you to pause this video, I want you to do that problem, and then I want you to unpause. Okay, hopefully you really paused. So now that you've done the problem, you would use the solutions video that I always make for you to check your answer. So you do the problem, and then immediately after, you would come to the solutions video to check your answer. So Eleanor had a z-score of 1.8, and Gerald had a z-score of 1.5. Eleanor's score is farther from the mean than Gerald's is, so Eleanor has the higher score. You want to write that statement in. Eleanor was 1.5 standard deviations above the mean, but Gerald was only Eleanor was 1.8 standard deviations above the mean, but Gerald was only 1.5. So if we're speaking of comparing between the SAT and the ACT, Eleanor did better. She was farther away from the rest of the average of people who took the SAT. Now do number 9. So pause the video. This is the last one that I'm going to have you do like this. Pause the video and try number 9. Oopsie. Okay, number 9 is like 3. So if you couldn't do it, go back to 3 and use 3 as your guide. Number 9 should be C as in cat. Number 9 should be C as in cat. So I am taking that little bit of time because there are so many resources available for you guys to be successful in this class, and I'm not sure that everybody is taking advantage of them. And if you would take advantage of them, you will be successful. There's no way that you're doing all of the can you do's, watching all of the solutions, and still scoring poorly on your quizzes. So part of that is have your can you do out and do one problem at a time. Have the can you do out and the solutions video open, do a problem, watch the solution, do a problem, watch the solution. That is going to make that process shorter and more effective. Then you know, coming to class the next time or while you're in class, where you have questions. So you do number 9, you watch the solutions video, you still don't get it, you raise your hand and have me walk over and help you. You come in early, you come in after school, you come in during lunch, and you tell me I don't get number 9 and we talk about it. There is no way you're scoring low on tests and quizzes if you're taking advantage of all the resources available to you. So take advantage. Okay, that's it. That's all she wrote. So, good job hanging in there. You got your can you do. You could do it. Love you.